In the first part of this video, we will introduce a trajectory which explains in some detail how the universe remains ripe and undiscovered even with the best capabilities of the world's masterpiece. The James Webb Space Telescope's main objectives include discovering locations of potential exoplanets. Until now, the largest number of exoplanets discovered by the telescope are those orbiting stars that are smaller and dimmer than the Sun. These usually have their Goldilocks zones at distances closer to their stars and shorter orbital periods than Earth. One reason for this is the main discovery technique used, called the transit method. This method involves detecting the dimming of a star's light as an exoplanet passes in front of it. It is easier to detect exoplanets that orbit closer to their stars because they transit more often. Additionally, smaller stars are dimmer, which makes the dimming caused by a transiting exoplanet more noticeable. Another reason for this trend is that it is difficult to find exoplanets that orbit stars similar to the Sun at similar distances to Earth. This is because an exoplanet must be aligned between its star and Earth's vicinity in order to be detected using the transit method. The probability of this alignment is less than 1%. The probability can be calculated by using trigonometry, since the Sun is 149 million kilometers away from Earth, and the Sun is 1.4 million kilometers in diameter. Then the angle range at which Earth can pass between the Sun and another star in a distant location should be less than 1%. This trajectory means that more than 95% of Earth-like planets in the universe remain hideous and difficult to discover. Even though James Webb Space Telescope seems to be the most capable telescope built in human history, its detection capacity of exoplanets similar to Earth is relatively slim. The scientific horizons in this field are still ripe. In Part 2, we talk about the limitations of interstellar space travel compared to planetary terraforming. Space exploration has been a source of inspiration and wonder for many people since 1957, when the Union of Soviet Socialist Republics, USSR, launched its first artificial satellite Sputnik. However, the harsh reality of the challenges and limitations that face us may dampen our enthusiasm and aspirations, since exoplanets are very far away and no habitable ones have been confirmed yet. As a primary example, the nearest star system, Proxima Centauri, is about 4.2 light-years away from us. That means that even if we could travel at the speed of light, which seems impossible according to our current understanding of physics, it would take us more than 4 years to reach it. This makes terraforming a more realistic and viable alternative to interstellar travel. Terraforming is the hypothetical process of modifying the environment of a planet or moon to make it more Earth-like and suitable for human life. Terraforming could allow us to transform some of the planets and moons in our own solar system, such as Mars or Titan, into new homes for humanity. Terraforming would require advanced technologies and enormous resources, but it may be within our reach in the foreseeable future. Interstellar travel, on the other hand, remains a distant dream for now. Most of the technologies and theories that have been proposed for interstellar travel are either speculative or impractical. Some examples are warp drives, wormholes, laser sails, and generation ships. These concepts may sound exciting and intriguing, but they also face many technical, physical, and logistical problems that have not been solved yet. Interstellar travel may not be able to truly answer the rising interest in space exploration until we overcome these obstacles. In Part 3, we talk about the theoretical limitations of interstellar travel as coined by Einstein and the practicalities which might prove otherwise. Einstein's theory might not be the final word on the nature of reality. There have been many attempts to test, modify, or even overthrow his theory, especially in the realm of quantum physics and cosmology. Some physicists have proposed that the speed of light may not be constant, but vary depending on the properties of space and time. For example, some studies have suggested that the speed of light may depend on temperature, or that it may have been different in the early universe. Beyond wishful thinking, cutting-edge technologies could soon put Einstein's claim under the microscope, especially concerning the limitations of interstellar travel. NASA's Parker Solar Probe, with its impressive recorded speed of 635,266 km per hour in the early stages of space exploration, might serve as a real-world test for Einstein's theories. This provocative development promises to be a significant milestone in the ongoing dialogue between science fiction and scientific reality. Part 4. Back to Earth. As we have seen, interstellar travel might not be a realistic option for solving the problems of a growing human population on Earth. Instead, we might be forced to consider other ways of stabilizing or reducing our numbers, such as population growth restriction policies. China was the first country to implement such a policy in 1979 with its booming population no other single country have ever experienced in the past. The Chinese government at that time introduced the one-child policy to limit its population growth. The policy was effective in reducing the fertility rate from 2.75 children per woman in 1979 to 1.62 in 2018. However, the policy also had negative social and economic consequences, such as gender imbalance, aging population, and labor shortage. In 2016, China relaxed its policy to allow 2 children per couple. Another factor to consider is the carrying capacity of Earth, which is the maximum number of people that the planet can sustain indefinitely. The carrying capacity depends on many variables, such as resource consumption, technology, and environmental impact. Different estimates have been made, ranging from 1 billion to over 1 trillion people. However, most experts agree that the current carrying capacity is around 10 billion people, which is close to the projected population size for 2050. This number was coined in a discussion paper by the UNEP Global Environmental Alert Service, GEAS, on June 2012, which reviews different estimates of Earth's carrying capacity. The paper states that the greatest concentration estimates falls between 8 and 16 billion people, a range we are fast approaching. The paper also acknowledges that the carrying capacity is subject to considerable uncertainty and variability, depending on many factors such as resource consumption, technology, and environmental impact. In conclusion, we have explored some of the fascinating and bi-fictional topics which highlights the probable amount of celestial livable planets compared to other options such as terraforming, and the pressing need for such developments spurring from the real-world Earth-related to space exploration, such as the James Webb Space Telescope, interstellar travel, and Earth's carrying capacity. This forces us to confront the realities and limitations of our own planet and its resources. Space exploration is a journey of discovery and adventure, but also of responsibility and stewardship. It is a journey that we can all share and participate in, as we seek to understand ourselves and our cosmic neighbors.